University of Paderborn. The title of his talk is Quantum Resonances and Scattering Poles. With this, I would like to invite him to really deliver his talk, and I also request all the participants to put their microphones. Okay, so over to you, Professor Hilgert.
Okay, thank you. Well, thank you for the invitation to give a talk in your seminar. I appreciate that, and so let me just jump right into it, but not before saying that whenever I use concepts, definitions that you're not familiar with, please just stop me and I'll try to explain better what I'm talking about. Okay, so my title is Quantum Resonances and Scattering Poles, and this is the outline of the talk. So I want to briefly explain what I mean by quantum resonances. I want to explain what I mean by scattering poles. Then I want to relate quantum resonances and scattering poles. And as my principal interest is harmonic analysis on locally symmetric spaces, these will be the key examples I will treat, and I will explain some recent results, and I want to advertise some not so recent but not so welcome work of Bunke and Olbrich on locally symmetric spaces of rank 1, which our key example is dealing with. And in the last section, I want to say something about higher rank, and there are technical problems, but there are also conceptual problems, and I invite everybody to think about these problems. So let me start by asking the question, what is a quantum resonance? Now, what is a resonance? Typically, when you look this up in Wikipedia, you'll see a resonance is a pole of a meromorphically continued resolvent. So you have some operator D, and you subtract the multiple of the identity. And if you have something that's away from the spectrum of the operator, then you have an inverse of such an operator. And if the dependence on the parameter z, which is a complex number, is meromorphic, then a pole of that meromorphic operator valued function will be called a resonance. Now, what's a quantum resonance then? Well, that you typically will not find in Wikipedia, so that's a homemade definition. It simply says if the operator has something to do with a quantum Hamiltonian, then I call it a quantum resonance. Why do I have this homemade definition? Well, one of my basic interests in the field is to relate quantum and classical mechanics, and you have similar situations in classical mechanics. And so I want to make a distinction between quantum resonances when you talk about a quantum Hamiltonian and a classical resonance, or there is a name for that in the literature, a real resonance when you talk about a classical Hamiltonian. So this is what I mean by quantum resonance. Now let me give the kind of key example that I want to talk about today. So let's think of the Laplace-Beltrami operator on a complete Riemannian manifold X. In that situation, this Laplace operator is essentially self-adjoint, and one can extend it as an unbounded self-adjoint positive. So my Laplace-Beltrami operator is a positive one, as a positive self-adjoint operator on the corresponding L2 space with respect to the volume measure. So that is the kind of operator I want to look at. And then I look at these resolvents, and to start out with, if you are away from the spectrum, then these are bounded operators on these L2 spaces. But what I want is meromorphic continuation, but the spectrum of such an operator contains a half-line. So there's no meromorphic continuations across this half-line if you do this as operators on L2 space. So what one wants to do is one wants to consider this operator as an operator from the smooth, compactly supported functions into the distributions, or what is basically the same, consider instead of the operator, its Schwarz kernel. And as a Schwarz kernel, as the saying, as a distribution on a product space, this thing can be meromorphically continued in some situations. And this is what I want to think about. So I meromorphically continue the family of Schwarz kernels around this complement, sorry, this complement of the spectrum, and I want to determine the poles of this meromorphic continuation. Now that's a very general problem, and it's not at all solved. So let's look at an example, a class of examples, Riemannian symmetric spaces of non-compact type. Now, we can make the problem now a little more specific. So I want to let X be such a Riemannian symmetric space. If I write it as G mod K, this is saying I have a semi-simple Lie group, real Lie group, non-compact G, and a maximal compact subgroup K, and the quotient is the Riemannian symmetric space. For those not working in symmetric spaces, just imagine the unit disk. Poincaré unit disk is good enough for many things here. So then I have the resolvent for the Laplace-Beltrami operator delta, and I modify it a little. So instead of writing just Z, I have something here that's the important thing about it. It's a quadratic polynomial. If the Riemannian symmetric space is of rank 1, we can write these actually as complex numbers, and the rho is a constant that always is called rho when you talk about symmetric spaces. For those who know, I don't have to explain, and for those who don't, it's just a constant. So one wants to show that this thing has meromorphic continuation, and then one wants to determine the poles and the residues of this meromorphic continuation. And that's a very specific problem, and it's been solved in only a few cases, really. So it's been solved in rank 1, first by Miatello and Will. In the 2000s, they solved it actually not for Riemannian symmetric spaces of non-compact type of rank 1, but they solved it for so-called Damek-Ricci spaces. And when Angela Pasquale and I looked at this problem following a suggestion of Maciej Zworsky, who had done the calculation for the unit disk, we didn't know about that paper. We used different methods, which turned out to be useful, so I quote it here as well. So in that case, rank 1, Riemannian symmetric spaces of non-compact type, one can explicitly determine all these poles and show that the residues, which are operator valued, are finite rank operators, and you can explicitly determine those as well. Now, following this paper on rank 1 cases, we were trying to solve the same problem in higher rank, and turned out to be quite difficult. And it took a series of papers to just solve it for most rank 2 cases. It had to be done case by case, and it was a pain in the neck. And we couldn't go any further. So some new ideas will be needed to solve this in higher rank. Now, this is an explicit invitation for ambitious young mathematicians to solve this problem in higher rank. Actually, I mean, if you read up on this and try to look this up, you find a paper by Mazzeo and Vasi, I think, and they claim to do just that. I mean, calculating the resonances of Riemannian symmetric spaces of higher rank, but they don't. I mean, they cut up the plane wherever a possible pole occurs, and they never go around. So they never really say that these are poles. They had the candidates for poles. We knew that too, but doing the meromorphic continuation is a different matter. Anyway, so this is what we have in that situation. And so what it says is quantum resonances as such are an interesting object. Now, what is a scattering pole? Now, what is scattering? Scattering basically is comparing asymptotics of evolutions for different time directions. So typically positive time, negative time to positive time, you have some obstacle. You only know asymptotic behavior, and you want to compare them in the past and in the future, and that's and comparing these solutions, that's scattering. And the scattering operator is the operator intertwining such asymptotic solutions of, for instance, a wave equation. And a scattering pole is then comes up as follows. So you have a parametrized family of equations. So parametrized, for instance, by frequencies. And then you get a parametrized family of scattering operators. And if you're able to show that this family depends in a meromorphic way on these parameters, then you want to look at the poles of that family. And in most examples that show up in the literature, there are some normalizations involved, and those poles will then be called scattering poles. Okay, so this is conceptually more involved than the resonances, but then there is a relation between the two. Okay, so what I want to give as an example as well for the symmetric spaces, and I want to tell you what these objects mean in the case of non-compact symmetric spaces. So let's do this as an example. So what kind of a wave equation do we want to look at? Well, we want to do the wave equation with the Laplace-Beltrami operator, and usual Fourier analysis methods, I mean, taking Fourier analysis in the time variable leads you to Laplace eigenfunctions, which you want to use to solve such equations. Then you notice in a Riemannian symmetric space of non-compact type, if the rank is higher than just 1, then these spectral lines for the Laplace eigenfunction will further split, because you have other invariant differential operators than just the Laplace-Beltrami operator. You have a finitely generated commutative algebra of invariant differential operators, invariant meaning being the operators don't change if you conjugate them by the group action. And so if you have such a nice commutative algebra, you have joint eigenfunctions, and they give the splitting of the spectral lines. So the harmonic analysis of symmetric spaces is really harmonic analysis of this abelian algebra of differential operator, not just harmonic analysis of the Laplacian. And the joint eigenvalues will be just characters of this abelian algebra. And for these characters, you have spectral parameters. And the parameters live in the dual of the complexification of a maximal abelian subspace of the P part of the Cartan decomposition of G. So what's important here for those not so familiar with symmetric spaces is we have a multidimensional complex parameter space in this situation in high rank, and in rank one meaning dimension of A is just 1. We just have complex parameters as we had them before, and in that case the algebra of invariant differential operators is generated by the Laplacian, and everything boils down to the Laplacian as before. Now, when we want to talk about scattering in this situation, then we need to introduce something like a boundary at infinity of the Riemannian symmetric space. And there are many different kinds of boundaries that one can look at. And in this situation, the first one wants to look at is the maximal boundary that also goes by the name of Fürstenberg boundary. And on this maximal boundary, and again, if you decided you want to think about just the Poincaré disk, then this will be just the circle, the topological boundary. In rank 1, it will be just a topological boundary of the Riemannian symmetric space. And then one has natural function spaces on this maximal boundary, and they are well known from the theory of spherical principal series representation. So these function spaces, I denote them by H lambda, and then one has operators between these function spaces, or between some of these function spaces, and those are the so-called Nabstein or standard intertwining operators. And due to the dissertation of Semyonov-Tianshansky from the 70s, one knows how to interpret these intertwining operators as scattering operators of the type that I explained before. And it's known, and you can read this up in the book of Wallach, that these standard intertwining operators depend on the spectral parameters lambda, and they form a meromorphic family of these operators. So in Riemannian symmetric spaces, scattering operators are something that has been studied for decades. So they are around, and there's a lot of information around. Okay, so I now introduced quantum resonances and scattering poles. And when you talk a physicist about resonances and scattering poles, then they will tell you, well, it's the same thing. Well, more often than not, when I ask physicists why this is so, I get some explanation of the sort, because they both mean that some incitation will cause an explosive reaction. So I want to make this a little more concrete. And there's a very nice explanation of this physics mantra in the book of Borthwick on spectral theory of hyperbolic surfaces. And I want to share this explanation with you. So let's start with resonances. So this is a wave equation. I mean, the notation is taken from Borthwick. It's I've kind of followed this for this talk in order to be able to use it. So I really talk about the Laplacian here on a hyperbolic surface or just the Poincare disk. And the constant rho is here 1/2, and so I get this 1/4. It's his formula, so don't worry about the 1/4 too much here. So this is a wave equation, and the right-hand side, the phi, is the driving force of the equation. So it's the background oscillation, and it's multiplied by some oscillation in time. And so let's study this a little. Now, what is the resolvent of this delta operator at some complex parameter of the form that I wrote? So 1/2 plus ixi. Well, that will be the modified resolvent. By the way, can you see my cursor when I move it around like this? I don't hear any response, so it seems nobody can hear this. Well, anyway, well, as I cannot see any pictures, maybe I get some reaction so I know that you're still there.
Yes, I can see the cursor.
Okay, thank you. Okay, so this is the modified Laplacian. I mean, he uses this modified thing, so it's the modified resolvent. So this is the resolvent at this quadratic expression in psi, and looks like this. So that's elementary calculation. And then what I want to do is I want to take this wave equation and get a solution. Now, if I apply just the Laplacian to the u, then I get this shifted thing plus psi squared u. And now if I write it in this form, I see that this formula u times this spectral t part times resolvent applied to the driving force will be a solution to the equation. And the only t dependence is in this harmonic oscillating term, in this e function, and that cancels this psi squared u part. So this blue thing, this blue equation down here, will be a solution for the driving force phi. And now you can see, if I'm approaching a pole of this resolvent in psi, then this right-hand side will explode, or it will go to infinity. This means I have a finite excitation, and I'll have a disproportionate reaction in u, in my solution. So this is what happens in a resonance. Now, what happens in the case of scattering poles? Now, again, I think of, say, the Poincare disk. I have a function psi at infinity that is, pardon?
Slides are not visible properly sometimes.
Pardon? Say it again, please. I didn't understand.
We cannot see it properly, the slide. Sometimes it's getting blurred.
Oh, okay.
Yeah, now it's fine.
It's better? Okay, thank you. So if we look at the scattering pole, we want to do the asymptotics in positive and negative time direction. So we have a background thing, psi, that lives at the boundary, that is the circle. Then we want this to be the the boundary value of some function inside. So I apply the Poisson transform. PS is the Poisson transform to that background thing, the asymptotics from the past. Then I have a function on the symmetric space, the unit disk, and then I want to understand the solution, and turns out that one can calculate that this solution has an asymptotic expansion. So in one asymptotic direction, it behaves like the psi that I have up to some normalizing function or constant. And then there is another asymptotic direction in the positive time direction. And that's this phi s. And then again, we see that if now, hold it, I want to write it like this. So the scattering operator now is take the asymptotics in negative time direction and map it to the asymptotics in the positive time direction. If there is a pole in the scattering operator, that means that given a nice bounded background in negative, in the negative time history, the positive time history will explode. So again, this is something like a resonance. So it's a very similar behavior for the resonance and the scattering, both times expressed by poles. So this is about the best you can get from physicists as an explanation why resonances and scattering poles are the same thing. Now, the problem is to make this mathematically rigorous in other situations. And so basically what I gave you, or what Borthwick's explanation is, this can be made rigorous for the unit disk, but for what other situations can you do it? And so I want to show you some results in this respect. So one result is by Guillaume and Zworsky, and they were interested in hyperbolic surfaces, non-compact hyperbolic surfaces, so that scattering makes sense in the first place. So they could describe the relation between resonances and scattering poles in that situation. Then there are two papers that came a little later. They also did things in higher dimensions. So they were talking about real hyperbolic manifolds. So hyperbolic surfaces are real hyperbolic manifolds of dimension 2. So they were, Borthwick, Perry, and Guillemot were talking about hyperbolic manifolds. And the techniques they were using allowed them not to just do locally symmetric spaces, but asymptotically real hyperbolic manifolds, which means that close to the boundary at infinity, so they look at a hyperbolic manifold, and then they do a boundary at infinity. They compactify the hyperbolic manifold as a manifold with boundary, and then they look at a at an open neighborhood of the hyperbolic of the boundary. And in this open neighborhood, they introduce nice coordinates, and that's where the name asymptotically real hyperbolic manifolds comes. So this uses coordinates, nice coordinates. And in that situation, they could also prove theorems relating quantum resonances in scattering poles. And for other reasons, a while ago, together with Sönke Hansen and APRG and Parthasarathi from your neighboring institute in Chennai, studied the rank 1 Riemannian symmetric spaces. So not quotients, not locally symmetric spaces, but global symmetric spaces. And we compared the quantum resonances that had been calculated before with the scattering poles, which in principle had also been calculated before or could be drawn out of the literature in terms of, I mean, taking the Napstein operators as scattering matrices or scattering operators. And we could compare those as well. So we had that. And in all three cases, the results we get, so I don't want to write precise results here, but just the gist of it is the following. Quantum resonances are roughly 1/2 of the scattering poles. And the other half are poles of unnormalized scattering operators, which in the Riemannian symmetric space situation are just the unnormalized Napstein operators. So they are not resonances. So mathematically, in a strict mathematical way, the physics mantra is wrong. But of course, I mean, when you talk to physicists, they will always say, that's not what I meant. These other half of the poles had to be excluded in the first place. So in that sense, it's correct, right? So I will be a little more precise a little later on. Okay, so let me, before I tell you what we have been doing more recently, let me tell you something about the technical tools one uses to do this. Now, the main tool for us in the Riemannian symmetric case situation was harmonic analysis, non-commutative harmonic analysis. And it does play in the other cases as well, and I will say some buzzwords a little later. So the basic idea is this. The resolvents live, or the resolvent, yeah, the resolvents live on the symmetric space or on the manifold I started out with. I said I want to rather not meromorphically continue the resolvent, but the resolvent kernels, it's Schwarz kernels. So they will be distributions on the product space x by x, x times x. So they live on x basically. Whereas the scattering operators, they relate distributions or hyperfunctions or functions on the boundary to, again, functions on the boundary, two different asymptotics. Now, when one looks at resolvents and scattering operators, what one realizes after a while is that the resolvent kernels living on the manifold as such have boundary values in a non-trivial way. And these boundary values are very irregular objects, in the worst case, hyperfunctions, on the boundary. The reason for this is that the resolvents satisfy differential equations, invariant differential equations. So this is something that has to do with the well-known Helgerson conjecture, where one says that functions or distributions or hyperfunctions on the boundary come as boundary values of solutions of equations, of eigenequations of Laplacian, and the operator between them is the Poisson transform. So the resolvent kernels have boundary values. That's not the complete truth. There are normalizing meromorphic functions involved that will play a role a little later on. But basically, scattering operators can be viewed or can be obtained via boundary values of resolvent kernels. So there is a relation coming from harmonic analysis. This is not only true for the symmetric spaces, it's also true for the locally symmetric spaces if they are nice enough, or these asymptotic hyperbolic spaces. They're also, using different methods, one can establish boundary values and a transform mapping functions on the boundary to functions on the manifold. In that context, they are sometimes called Poisson transforms, but they're also called Eisenstein transforms sometimes, but it's basically the same thing. And so Borthwick and Perry, they used this Melrose type microlocal analysis using their coordinates. We used this pure version of harmonic analysis because we studied these more explicit or simpler, in some ways, simpler or more symmetric situation of Riemannian symmetric space. But then there is another method that one can use and that had not been used before. And the point of our paper is actually a proof of principle that in such a situation, one should use what I call the Bunke-Olbrich theory. So they have in the 90s, Ulrich Bunke and Martin Olbrich studied, motivated by something called the Patterson conjecture, which came from analytic number theory and had to do with dynamical zeta functions. They studied rank 1 symmetric, locally symmetric spaces, which could be viewed as manifolds with boundary. And they introduced some really neat tools. And for locally symmetric spaces of the same type, one can use their theory to give new results on the relation between quantum resonances and scattering poles. Let me say a few more words on this Bunke-Olbrich theory. So this is a theory that works for rank 1 spaces, which are for locally symmetric rank 1 spaces where the discrete group that one mods out is convex co-compact. I don't want to go into the details of what a convex co-compact discrete subgroup is. These hypotheses basically mean that if you take the quotient by this discrete group, then the result will be a manifold with boundary. For technical reasons, they had to restrict themselves to classical spaces. So there's only one rank 1 space or family of rank 1 locally symmetric spaces that's not covered, that comes with F4. So that's out here for technical reasons. They probably could be solved, but not in the spirit, not the same way they were dealing with it in their papers. Okay, so now we have the quotient, the locally symmetric space, and it's a manifold with boundary. And one can describe this boundary. It again is a quotient, but it's not the quotient of the boundary of the symmetric space, which in this rank 1 situation is a topological boundary. It's only, I mean, the thing that I have to take the quotient of is just an open subset of the boundary. And more precisely, it's the complement of the limit set. Well, the limit set is an easy concept. So if you take just any point in the symmetric space, and now you take your discrete subgroup. It will be infinite because it's convex co-compact. Then you take the orbit of this one point, so you have an infinite set. And then you take the limit points in the boundary of that orbit. Doesn't depend which point you started out with. It's always the same limit set that you get. That's the so-called limit set of a discrete subgroup. That's a well-studied object in dynamical systems and number theory and harmonic analysis. And the complement of this closed gamma invariant set in the boundary is an open gamma invariant set in the boundary, namely this omega. Now, the point is that the gamma acts properly discontinuously on this open set. And since it was torsion-free, the quotient will be a manifold. And that turns out to be the manifold we have to take as a boundary for the locally symmetric space in order to compactify it as a manifold with boundary. So we have that. Now, Bunke and Olbrich, in their paper, they study this situation, and then they study the spectral theories of the corresponding Laplacians on X and the quotient of X on the symmetric space and the locally symmetric space. And they also study resolvent kernels and scattering operators in this context. And here's the main technical construction they have. What they do is they look at distributions on the boundary. Remember, in all the examples we had before, the scattering operator and everything, we had to have distributions or nice situation or distributions or functions or maybe hyperfunctions on the boundary. And what they do is, in order to study them for the locally symmetric space, they lift the situation to the global symmetric space. Now, you can pull back distributions if you have a nice quotient, so that is not so much the problem. That's a standard procedure. But then you have a distribution on this open subset of the global boundary. And then the key insight they have is that you can find an extension of such a distribution to a gamma invariant distribution on the entire boundary. Now that's a non-trivial thing, and it's even more non-trivial to show, as they did, that if you have, if you do that for different spectral parameters, you can do this construction of an extension of distributions as a parameterized family. So you look at all the distributions you can get as boundary values of eigenfunctions of the Laplacian. Then you have a parameterized family of distributions on omega. And you extend this in a meromorphic way to get a parameterized meromorphic family of distributions on the boundary upstairs of the symmetric space. So that's what they do. And in this way, they enable you to compare the global, resonant, resolvent kernels and scattering kernels, scattering operators of the global symmetric space and the locally symmetric space. And so since they had the methods to compare the two, and we have very precise results for the global symmetric space, we can take the results from the global symmetric space and use what we know in which way the boundary values of the resolvent kernels turn out to be the scattering kernels in order to prove a theorem for locally symmetric spaces as we had it for globally symmetric spaces. It's not quite as strong as the global theorem for two reasons. One is we have to take out the exceptional set of those spectral parameters where the Poisson transform is not bijective. So that's a problem that in the long run will certainly be fixed as it was fixed in the global symmetric space case. And then it's not as precise in some other sense. I will say something about that later, but otherwise the result is the same as before. Quantum resonances are essentially 1/2 of the scattering poles. In a little while, I will make the essentially 1/2 more precise, but I want to make some remarks first. In the case of asymptotically hyperbolic spaces that Borthwick and Perry and Guillemot and Giuppe-Zworsky have, there are also results about the multiplicities of these resonances. I mean, the dimension of these generalized eigenspaces that you find there. We don't have that yet because, we were not able to easily prove it, but we do think that the methods that Guillemot used to calculate multiplicities could be used in our situation as well, but it would have made the paper disproportionately longer to do this. And since our goal really was to show the use of the Bunke-Olbrich theory, this would have sort of gone lost in a long and technical paper where a major part of the paper is just repeating techniques that had been used elsewhere before. So we didn't do this. But let me say a little bit about what does it mean to be essentially 1/2 of the scattering poles. Now, what you see here is kind of the difference between a true resonance and a modified resonance. So if on the right-hand side, you look at Z, that's just spectral values, and the spectral value is to be taken as rho squared plus zeta squared, as in one of the very early slides in this talk. And those will be, so the zeta will be basically the spectral parameters. And the green part, on the real line in the right-hand side picture, that's just the spectrum of the Laplacian of such a locally symmetric space. I mean, yeah, of convex co-compact. So there is an absolutely continuous spectrum starting at rho squared, going off to infinity. That's this light green line. Then there are finitely many eigenvalues. There might be embedded eigenvalues as well. So I'm not talking about that. And now I want to look at the spectral parameters zeta, and they are on the left-hand side. And so the left-hand side, these are the parameters with respect to which I do meromorphic continuation for resolvents and spectral operators and so forth. So that's happening on the left-hand side. So let's see, where do I find the original spectrum of the Laplacian? It's the real line here. Those go to the right-hand ray on the right-hand side. And then there are these finitely many dots here. They will be eigenvalues. And I take the last dot, and then I take everything above this last dot. So that's the blue thing. And let's see what's happening on the right-hand side. So the blue thing gets mapped to the blue thing on the right-hand side, and the blue line separating this from the rest, that's this blue parabola here. And now the statement of the theorem says the scattering poles that are not in the physical, I mean, that's what's called the physical half plane, that are not in the physical half plane, those will be the resonances. So when you calculate scattering poles and resonances, you have to determine what this last eigenvalue is. And whenever you have a scattering pole that's not upstairs in the blue part, but it's downstairs, then it will be a resonance. And all the resonances show up in this way. So you have a precise result as far as the location of resonances and scattering poles are concerned. Okay, so this is the result that we have there. I wasn't all that precise in the statements of the theorem. One reason being, I mean, it took us quite a while to get the statements because in the literature, I mean, we're putting together results, previously known results. I'm not saying there is, I mean, there's some ingenious idea going on in this paper. So we are putting together what one knows about rank 1 symmetric spaces, what Bunke and Olbrich worked out for classical locally symmetric spaces of convex co-compact type, and well, standard harmonic analysis, basically, or some knowledge about Poisson transforms. So that's basically what we use. But when you look at the sources, you see that there are millions of different normalizations in the literature and conventions you can use. And so it took us quite a while to compare the conventions, to translate conventions into one each other in order to not to make stupid mistakes in using one result in a different context. And so I didn't want to go into these technicalities at all. But I want to show you one thing that is an independent result that we were quite surprised about, and which one can formulate in a precise way here. And that's an abstract lemma about elliptic operators that we needed to prove our result. And it goes like this. So you take a smooth Riemannian manifold M, an elliptic operator P of positive order, so non-constant. Then you look at the resolvent, and you assume it exists on some open set and can be extended to a larger open connected set as a meromorphic family of operators, as we did before. And then a point in that open set is a pole of the Schwarz kernel of this extended meromorphic family of operators, if and only if it's a pole of that distribution that gives the Schwarz kernel when you take out the diagonal. So you do not pick up extra poles when you add the diagonal, or you don't lose poles by not considering the diagonal. So the reason we needed this was that when we switch between operators and Schwarz kernels, and we do boundary values, then for the boundary values, we only get results away from the diagonal. And in order to, since we're interested in the location of poles of some meromorphic object, the result would have been completely killed if the diagonal would cause extra poles. So if we needed to control that, and turns out it's possible to control that, and I don't know, this lemma is maybe known to specialists, but we couldn't find anything like that in the literature. So this is what we needed. And maybe if you're not interested in the theory of resonances or scattering poles, maybe this is a lemma to take home from this talk. Now, I have 2 minutes, if I'm right. Let me say a few words about higher-rank symmetric spaces. Scattering operators, as I mentioned before, in higher-rank symmetric spaces can be interpreted as, can be obtained from Napstein operators. So that's Semyonov-Tianshansky in his dissertation from '76. Then invariant differential operators show up. They replace the Laplacian, as I explained before. And this modified resolvent, I mean, you may have wondered why one has these quadratic polynomials. Well, it's a standard thing people do when they analyze the Laplacian, but here's a reason why one wants to do that, because this quadratic polynomial basically is the Harish-Chandra isomorphism image of the Laplacian. So this is what you have to do in general. So it's the right way to consider the symbol of the Laplacian. So this is what comes about. So this is what one can easily do for higher rank symmetric spaces, but here comes the problem. Now, what is the resolvent? Now, if we want to, I mean, we can try to do the resolvent for the Laplacian, but it doesn't seem to be right. And the difficulties we saw in doing, in calculating quantum resonances for higher rank is an indicator that one really wants to look at something that is defined for the entire algebra of invariant differential operators. So what should that be? What's the resolvent of a commutative, finitely generated algebra of operators? So that's a conceptual problem. If any of you has an idea, I would be grateful to hear that. On the other side, on the classical side, we were able to solve this kind of problem by circumventing it to do classical resolvents in higher rank. That could be done because of the very specific situation we face for the classical mechanics here. But the general problem is wide open as far as I can see. And for locally symmetric spaces, we do not have a Bunke-Olbrich theory for higher rank analogs of convex co-compact locally symmetric spaces, which would be Anosov groups. That's an active area of research in the last 20 years or so. But we don't have a Bunke-Olbrich theory there. And we do not have a scattering theory in the spirit of Semyonov-Tianshansky using multi-temporal wave equations in higher rank. So we only have something for the global symmetric space. We don't have anything for locally symmetric spaces. Well, with these open problems, missing ingredients, I finished this talk. Invite you, or my hope is that I got some of you at least interested into this kind of problem, and I thank you for your attention.
Thank you, Professor Hilgert. Okay, are there any questions from the audiences? Okay, so I have one or two questions. So the thing is, you have written that if the operator is Laplacian minus rho square minus zeta square inverse. Okay, so it is solved for most of the rank 2 group cases. So what does that mean? Most of the rank 2 means which groups actually you have solved this thing?
I acoustically didn't completely understand the question. Could you say it again?
So you told that if this operator is Laplacian minus rho square, okay, minus zeta square inverse, okay. So you have really found that what are the resonance of this thing for most of the rank 2 cases, okay. So most of the rank 2 means which thing actually it is really. So can you clarify that what do you mean by most of the rank 2 means? You know which
well,
is it?
Yeah, it's so there is no result that I know of that in rank more than 2 anybody has proven what the resonances are, right? And nobody has really given the meromorphic continuation. So what Matteo and Vasi do is they do a meromorphic continuation, but they do a covering of cut planes, and whenever they reach a point that is problematic, they cut from infinity, and then they never go around this possible pole. So they never prove that these candidates for poles that one has actually are poles, right? So they just they spiral up, and so they don't treat the pole so they don't do this. And the reason we couldn't make any progress there is this. So our approach was to use the inversion formula for the Harish-Chandra-Helgason Fourier transform. And when you do this, what you have is you write an integral. I mean, you write the resolvent as an integral, and the integrand has this complex parameter inside, and then you want to analytically or meromorphically continue that integral, right? And in rank 1, this was easy because all you had to do is you had to do a contour shift, and you passed the possible poles, and then you could do a contour shift that picked up some residues, and this is how you did that. And that was fairly easy. Now in rank 2, you have an integral, and now you have a 2-parameter family, and the contour shifts were a lot more difficult, and the reason is that the singularities of the integrand were no longer discrete, right? They are now continuous, and you have to make sure that you have some way of changing the contour that does not hit the singularity. So, and while by shifting you can go beyond a discrete singularity, shifting a contour does not help you avoiding a priori a no longer discrete singularity. So in rank 2, we could get around this finding suitable coordinates and then explicitly write what the contour shifts or what the changes of the what the change contours should be. But in higher rank, we didn't see any systematic way to do these shifts, right? So it seemed to us that some idea is necessary. And here's, I mean, my gut feeling is if you do the right thing, not only to the Laplacian, but work with with a complete set of generators, then you have less singularities because you cut out a dimension for each generator. So it might be possible to reduce the problem to something where you have a discrete set of singularities again. And then you might be able to see what kind of a shift you need, right? But we were not able to make this work, and I couldn't convince Angela that this is a path worthwhile following. So
okay.
So
yeah, okay, Antardeep, you have a question? Antarif, okay, Antarif Mandal. Can you turn on your video?
Hello.
Yeah, can you turn on your video, Ajwal?
I just did. I don't know if.
Yeah.
Hello, sir.
Okay.
I wanted to ask that, like, what is it with the complex symmetric spaces? Has there been any result on this in that direction?
Well, I mean, there are two possibilities to view complex symmetric spaces. I mean, if you can, of course, take a complex symmetric space, view it as a real symmetric space, right? But you are after looking a Casimir operator for a complex symmetric space, which then will no longer be positive, right?
I mean, it extends the analysis on the real symmetric space with the complexification. It extends to something very similar. And what we have seen is like the harmonic analysis on complex symmetric spaces is often much easier than the one in the real symmetric spaces.
Yeah. Okay. So in so then you do mean the Laplace-Beltrami for
Yeah,
the
Laplace-Beltrami.
complex symmetric space viewed as a real manifold.
Yes.
Yeah. Okay. Yeah. Typically, I mean, we know that we have explicit formulas for, say, spherical functions in that case, and many things behave in a similar way to, I mean, are in a similar way easier than the general case, as rank 1 is easier than
Yes.
the general case. So I'm not aware that anybody tried to calculate resonances for the complex case. We certainly did not explicitly try. But I mean, one reason, I mean, that's very similar to what I just said. If you do this, then if one wanted to use our method, turns out, I mean, if you do the Harish-Chandra Helgert transform, the formula, the inversion formula, or the integrals are a little simpler from the general case, but not very much simpler, because I mean, in the denominator, you just have some polynomial. It doesn't get a lot simpler as far as I can see. So the same problems still are there, because you are in higher rank automatically, and you have this problem about shifting contours. So I mean, our method doesn't seem to be simplified by the hypothesis to work with a complex symmetric space. Other methods may very well be. So I don't know. But I'm not aware of any paper that does it.
Okay. Thank you.
So are there any questions? No. So if there are no questions, let us thank the speaker for a nice talk. Okay. With this, we will end this session. Okay.
Well, thanks again for your attention.